Now we've already seen one way that atoms can emit light. If an electron in the atom is excited up to a higher energy level, then when it falls back down again to the lower energy level, the energy that it loses is emitted as a photon. But there are other reasons that atoms emit light. And one of those reasons is because of the material's temperature. Now, nothing in the universe is actually at 0 degrees Kelvin. And so everything, all matter in the universe, is emitting EM radiation. And the weird thing is that it's emitting EM radiation at all different wavelengths. So yes, I am saying that my pen, me, the table, we are all emitting gamma rays, radio waves, microwaves. The caveat, of course, is that we're emitting some of them massively more frequently than others. Now, at this point, we're going to stop talking about pens and tables, and we're going to talk about something called a black body. A black body is a theoretical concept, so it's a bit like a point particle or an inextensible string, a frictionless surface. They don't really exist, but they're sort of idealized concepts. So a black body is something that is a perfect emitter and a perfect absorber. Now, that means that it absorbs absolutely all wavelengths that fall on it. Any EM wave that hits it is absorbed. And it emits all wavelengths without any kind of obstruction from its surface or anything like that. So perfect emitter, perfect absorber. So if you measure the amount of light coming off a black body for each wavelength, so you detect all the light coming off it and then you measure in a certain amount of time what was the intensity of this wavelength, what was the intensity of that wavelength, and you plot it, you'll get a nice curve like this, and this is called the black body curve for the object. And what you notice is that there's a peak, a single peak, smooth curve with a single peak. Now, if you were to heat up that black body to a higher temperature, you would notice two things. One is that you get more of every wavelength coming off. So my curve is going to get taller. It's going to be higher at every point. But also the most common wavelength is going to change. So if I heat up this object, I'm going to end up with a curve, say there. So I've got more of every wavelength, but also my most common wavelength has moved. Okay, this most common wavelength, which we call lambda max, is directly related to the temperature of the object, so long as you've measured that temperature in Kelvin. And this is what's described by Wien's displacement law. Now, I've no idea if I'm saying that name right, but I'm going to say Wien, but you say whatever you say. So here is the law, and it tells us that the most common wavelength is directly proportional to the inverse of the temperature, and remember, very importantly, that temperature must be measured in Kelvin. Now, the actual constant, so the most common wavelength, is actually equal to, I think it's that over the temperature in Kelvin. But your example doesn't tell you this. It doesn't give you this constant because it wants you to do all sorts of like ratio questions. So instead it tells you the law with its direct proportionality symbol. And so here's a pretty typical question. So in this question they're asking you to test whether or not lambda max is directly proportional to 1 over the temperature. Okay, so you need to prove that it's proportional. Have a go at that now. Okay, and the way that we prove whether or not something's proportional is we work out what the constant is. So as we said before, lambda max is equal to some constant over the temperature in Kelvin. Okay, so you are just going to work out what is K for every row of the table. And so I've got this. Now, notice it doesn't really matter that it's in micrometers there, because all you're looking for is the proportionality. Okay, and so the first mark is for working out these values, and the second one is for saying, yes, this data does support Wien's displacement law, because all of these k values are 3. So they're all 3 to 1 significant figure.